Welcome to Mathematical Physics. Today, we are going to explore one of the most powerful and beautiful tools in all of mathematics, the Taylor series expansion. If you have ever wondered how your calculator instantly knows the value of sine, cosine, or an exponential function, you are about to find out. This concept is the bridge between complex, winding curves and simple, easy-to-calculate polynomials. By the end of this video, you will understand not just how to use a Taylor series, but exactly why it works and why modern physics relies on it so heavily. Let us dive in. To understand what a Taylor series is, imagine you are driving a car at night on a winding, pitch-black road. Your headlights only let you see exactly where you are right now. If you want to guess where the road goes next, what information would you use? First, you would use your current exact position to know where you are starting. But position alone is not enough to predict a curve. You need to know where you are headed. Then you would use your current direction and speed to guess a straight line path forward. This is the first step in predicting the unknown. Now that we have our position and straight line direction, how do we predict the curves? If you want an even better guess, you would feel how the steering wheel is turning. This turning represents your acceleration, allowing you to predict a curved path. This is exactly what a Taylor series does in mathematics. It takes a complicated, winding mathematical function and predicts its entire shape just by looking at its position, its slope, and its curves at one single starting point. By gathering more and more information at that one spot, we can map out the entire journey. So, how do we build this mathematical prediction? In formal mathematical terms, a Taylor series is a powerful method used to represent a complex function as an infinite sum of simple polynomial terms. Why polynomials? Because a polynomial is just a mathematical expression with variables raised to whole number powers, like x squared or x cubed. These are incredibly easy to add, multiply, and integrate. By taking higher and higher derivatives, we capture more and more details about the function's curves and wiggles. If we add up an infinite number of these polynomial terms, the resulting series will perfectly match the original complex function. You might be wondering why we need to turn perfectly good functions into infinitely long polynomials. The truth is, calculators and computers do not actually know how to calculate functions like sine, cosine, or exponentials directly. Instead, they use Taylor series to turn these complicated functions into simple addition and multiplication problems that their microchips can process instantly. Furthermore, in physics, we constantly use this tool to simplify impossibly hard problems by cutting off the infinite series after just one or two terms. Without this mathematical tool, most of modern physics and computer science simply could not exist. Now that we understand the goal, let us look at the mathematical engine behind it. This is the general formula for a Taylor series expanded around a specific point. We want to approximate our unknown function, f of x, using its value and its derivatives exactly at a starting point, a. Let us break down the symbols. The term f of a is the exact height at our starting point. The derivatives, f prime and f double prime, tell us the slope and the curvature. The exclamation mark represents a factorial, which naturally appears from the calculus rules of integrating polynomials. Finally, the x minus a terms measure how far away we are moving from our safe starting point. As this distance increases, we need more terms to keep the approximation accurate. This formula we just saw is incredibly powerful. But it can be simplified. Very often in physics and mathematics, we choose our starting point to be exactly at the origin. This means we set our center point, A, equal to 0. When we plug 0 into the Taylor series formula, all those x minus a terms collapse into just x. This simplifies the equation beautifully into what is known as the Maclaurin series. It is exactly the same concept, predicting a function using its derivatives, but specifically anchored at the y-axis. Let us see what this cleaner formula looks like. Applying this 0 center point, here is the Maclaurin series formula. Notice how much cleaner this looks. Because a equals 0, the distance term just becomes x. This formula tells us that if we know the value of a function and all its derivatives at the origin, we can build a polynomial that mimics the function everywhere. The first term, f of 0, is simply the y-intercept. The second term tells us the initial slope. The third term tells us how the graph bends right at the y-axis. As we add higher powers of x, we are adding finer and finer adjustments to our polynomial curve. If x increases, the higher power terms become much larger, which is why we need them to maintain accuracy far from the origin. Before we move on, let us see this with a concrete example. Let us find the Maclaurin series for the exponential function, e to the power of x. Our goal is to turn this exponential curve into a polynomial. First, we evaluate the original function at 0. Any non-zero number raised to the power of 0 is exactly 1. Next, we take the first and second derivatives. The beautiful thing about e to the x is that its derivative is always just itself. So every single derivative evaluated at 0 will also equal 1. Now we simply plug these ones back into our Maclaurin series formula. Every derivative term becomes a 1, leaving us with this beautiful, elegant, infinite sum. This means the complex exponential function is perfectly equal to this simple polynomial. Now that we have successfully expanded the exponential function, let us try something that oscillates, the sine function. This is incredibly important in physics for analyzing waves and pendulums. We evaluate the function and its derivatives at 0. The derivatives of sine cycle through a predictable pattern: sine, cosine, negative sine, negative cosine. When we plug in 0, notice a fascinating pattern. All the even derivatives contain a sine term, which becomes 0. All the odd derivatives contain a cosine term, which alternates between 1 and negative 1. This means every even-powered term completely vanishes. Plugging our non-zero terms into the formula gives us the Taylor series for sine, containing only odd powers of x. This perfectly matches the fact that sine is an odd function. So we have proven that the sine function can be written as an infinite polynomial. This brings us to a crucial derivation in physics. What happens when the angle x is very small? Let us set up the reasoning. We start with the full Maclaurin series for sine that we just found. Now, imagine a pendulum swinging back and forth just a tiny bit, meaning the angle x is a very small fraction, close to 0. Mathematically, when you take a tiny fraction and raise it to a high power, like 3 or 5, the result becomes microscopically small. We are establishing the foundation to see why complex physics equations can suddenly become very simple. Continuing our derivation, let us look at those higher-order terms. Because x is so small, terms like x cubed and x to the 5th power become incredibly tiny. In fact, they become so close to 0 that they have almost no impact on the final calculation. Therefore, we can safely ignore them entirely. By chopping off the infinite series after the very first term, we are left with a beautifully simple result. Sine of x is approximately equal to x. This is the famous small angle approximation. It is the exact mathematical intuition that makes solving pendulum equations possible. We have used the rigorous Taylor series to justify a practical physics shortcut. Now that we have used this formula and proven its approximations, let us understand what it looks like visually. Look at this graph. The black wave is our original sine function. The straight red line passing through the origin is our first term, y equals x. Notice how it perfectly matches the sine wave right at the center, which visually proves our small angle approximation. But as we move away from the center, the red line shoots off. To fix this, we add the next term to get the blue curve, which bends down to hug the sine wave further out. Adding yet another term gives us the green curve, which wraps almost perfectly around the sine wave for an even wider range. Every term we add forces the polynomial to match the true function over a larger distance. We have covered a lot of ground today, so let us reinforce the most important ideas. First, a Taylor series is a powerful mathematical bridge that translates complex, difficult functions into simple, manageable polynomials. Second, it achieves this by using the function's value and its derivatives at a single known point to project its behavior outward. Third, when we center this expansion exactly at 0, we call it a Maclaurin series. Finally, remember that the more terms we include in our polynomial, the further away from our center point we can accurately predict the function's value. You now have an absolutely essential tool in your mathematical physics toolkit. Great job following along.